Hello, good morning, students. So today we will talk about the roots of algebraic and transcendental equations. And in our lecture class, we talk about in detail what are the roots and what are different type of algebraic and transcendental equations. If an equation involves x, y, z, and their higher power, we term them like algebraic equations. If there are like a sine, cos, tan, e raised to power something, exponential, or log, anti-log, we term them as a transcendental equations. So let's say if we have an equation and any equations or any function f of x, the point at which that function gives us zero value, that point is known as the root of that particular equation. In this chapter, we're gonna cover four different methods. One is bisection method, iterative method, method of false position or regular falsi method, or Newton method. These four different methods, we will use it and we will try to visualize it in R as well. So let's go quickly to our numerical problem and solve it in R. So in our in our theoretical class, we try to understand what is a bisection method. So for example, if a function is noted by this solid line, we try to have an interval A and interval B. And we try to look the value of the function is changing like positive or negative in this two interval. For example, at point A, the function fx is negative, but at point B, the function fx is positive. So we can say that the root of this particular function fx lies between A and B. Then what we will do, we will take the average of A and B and we will try to estimate in the next iteration. And then this will go on and go on. Ultimately, we will reach to this point of intersection of this x-axis and that particular solid line or this function. All right. So I recommend you guys read the notes and chapter of the book, chapter number 1 of the book. So let's go quickly and try to solve an example to visualize our roots of real roots of the equation. So in this example number 1, they say that find the real roots of the equation x log tan uh, x minus 1.2 by bisection method. So we will use bisection method and we will try to visualize it. Our first task is to check that in which interval our function fx is changing its sign. All right, so let's say we have a function fx x log tan x minus 1.2. If I put the value f of 1, then they give like 1.2. Then f of 2, it gives me minus 0.5979, and then f of 3, it gives me a positive 0.2313 up to 4 decimal places I'm just using. And then again, if I go with f of 4, it is already giving me 1.2100. So I will choose an interval f of 2 and 3 because in this interval, my the signs of x are changing. This is minus and this is positive. So let's try to visualize how it works. Let's say we have x. So let's try to create a sequence of x is equals to sequence. Maybe we will start with 1, comma 4, and let's say length out is equals to 20. So it will give you from 1 to 4, 20 equal values. So let's run this one. Or you can just say that from 1 to 4, give me 5 equal values, 1, 2, 3, 4, and maybe you will get another value. But let's just put it like 4 equal values. So I will get maybe 1, 2, 3, 4. So let's check what are the corresponding values of y, which is equals to our function x log 10 x minus 1.2. So let me create y, which is our function, and it will be like x multiplied by log of 10 and log of 10 and x and minus 1.2. So for different values of x, I get the values of y. So let's check the values of x and let's check the values of y. All right. So before I further go, let's try to delete this portion and this portion. It is always a good practice just to delete, and again just try to delete in here as well. So let's just run it again in x and y in here. So let's see what is your x. Just run x, and then what is your y? We run this one. So at 1, the value is minus 1.20. So in here you can see that our answer is correct. So at 4, it should be 1.21. So up to 2 decimal places, it was 1.21, but you can just update it later on. But the values in R, they are more precise. All right. So let's try to make a plot in here. So in at 1, it is minus 1.20. At 2, it is minus 0.59. And at 3, it is 0.23. So we can see that our interval is between 2 and 2 and 3 because our sign is changing. So we got the same results when we were solving the numerical problem in the class. All right, so let's try to plot it. So in R, you can use a plot function to make a graphical representation. So I will just write it that here f of 2 and f of 3 are opposite signs. And then let's try to use the bisection method and find the solution. So because I want to have like both sides, so I have just bear with this like small screen in here, small window. Okay, so let's try to plot it. So I will use the plot function in R. So you will see that plot graphics. You will use the plot function in R and just to write the values of X and corresponding values Y. If ever you try to run it, you will see that at your right hand side at the bottom right, so you will see a plot showing X and corresponding values of Y. But I want to make it like I want to present it in a better way. So let's try to add new features in here. So I want to see that my plot should be aligned. So let's use the argument type is equals to L. This is L, not 1. So it will give you line plot. Let's run this one. It will give you a line. If you want a point, just run P and it will give you points. If you want both, just run B and it will give you both. So I prefer a line plot in here. Moreover, I want to change the color. So I would prefer color is equals to maybe red. So let's run it again. Also, I want to have like the width of the line width should be equals to maybe 2 to look better for me. I run it again and I am modifying it. Also, I want to control the labels on the x-axis and y-axis. For x label, I would say that maybe x values. And for the y label, I would say that maybe it will be a good idea. I will just write the equation. Okay, let's see. I can say that f of x, sorry, f of x is equals to this one. So let's run it again. So in here, you can see that f of x is displayed on y-axis and x value is displayed in here. Okay, so let's try to run everything again and try to understand. Now I can see that my value is changing somehow like between 2 and 3 because this is my like x-axis. So let's try to plot x-axis as well. So we can do it by using the function AB line in R. And if you want to plot a horizontal line, put it H, it should pass through 0. And also I want the color is equals to black. And I want that line type line type is equals to 1, and I want line width is equals to 2. So I will run this one. So this line is added. Now it is quite visible in here that my roots lie somewhere between 2 and 3. It did somehow it looked really good if you add the grids. So it will give you a better like view. Let's try to add the grids in our plot. So I added the grids by using the function grids. So every time once you run, the grids will be added in here. And then I can see that my roots are between 2 and 3. So let's try to make an interval. Again, I want to have like AB line. I want to draw a vertical line which is equals to which that can pass from 2, v is equals to 2, and color I want to have a color equals to green maybe, and maybe I can say that dark green, and line type is equals to 2 and line width equals to 2. So there is a vertical line that passes 2 through 2. In a similar way, I can do it by adding just 3. Another line is added. So now I am very sure that in this interval 2 and 3, my root exists. So In here, in our first approximation, what did we do? If you see the slides in here, that in our first approximation, we take the average of 2 and 3 and that try to visualize that where the roots exist. So I want to apply another line. I want to add another line at 2.5 and run it. So if you feel like confusion, like which line is this one, we can we can add the text. For example, maybe we can add the text in here at x is equals to 2, and then we can add another text in here, x is equals to 2.5, and another text I can add it in here by running this one. Now, it is not necessary that you add it, so I'm just gonna deactivate it like for later. I will not run it again and again. It's just to for your understanding that how my lines look like. Now it is quite clear that my root lie between 2.5 and 3. So after my first approximation, once I go my second approximation, I said my root is between 2.5 and 3. Right? So what I am gonna do is that I will go back again and I will say that my interval should not be equals to 1 and 4. Now I am 100% sure that my interval is between 2 to 3. And I want take like somehow 20 values between them so my graph will look little bit better, and I run it again. So it is very visible in here, very visible. Now, one problem you will face that when you keep changing these kind of things, um, your the limits on x-axis and y-axis, it will change in a dramatic way. So what I'm gonna do is I will limit my x-axis and y-axis values. How? Let's add x limit. I would say that the minimum value from x, the minimum value from x should be my lower limit on this side of x, and the highest value, which is max of x, should be at my upper side, left side and right side. So I just added this argument. In a similar way, I can add y limit. I will just copy and paste in here. Okay. And instead of x, I will just put y. So I will run it again. I run it again, again. This one. Now you are trying to control your everything. So with time, you will realize that you are somehow controlling your axis. So after first approximation, let's go to our second approximation. We are done with actually with the second approximation. And let's try to visualize our second approximation. In second approximation in here, you see that your root lie between 2.5 let's say this is somehow 2.5 and 3. So instead of 2, I would say that 2.5 and 3 and run it again. So now from here, I am very sure that my root is between 2.7 and 2.8. But in bisection method, the rate of convergence is very slow. Once I use the third approximation, it is saying that your root lie between 2.5 and 2.75. And it is true. My root is between 2.5 and 2.75 somewhere here. So if ever I change my this particular limit to from 2.5 and 2.75 and run it, so my root is somewhere here, that limit is 2.75 and I reach somewhere here. And in our next approximation, in the fourth approximation, they say that my root is between 2.625 and 2.75. So instead, I would 2.5, I will just change it to 2.6 to 5, and I'm gonna run it again. Now it is clear that my root is somewhere very close to 2.74. Again, I am telling you that in bisection method, the rate of convergence is very slow. So we need to go with the another approximation. In next line, next approximation, they say that change the interval 2.6875 and I'm gonna change it to 0.6875, 6875 and run it, run my code. And in my sixth approximation, my root is between 2.7185, so 2.7185 and 2.75. I'm gonna run it again and visualize. So now, students, if ever I say you that up to one decimal place, my answer is 2.7 because this portion, this represent 2.7 as well. This one, everyone is representing 2.7. But in the second decimal places, it is changing. It is 2.720, 730, 740, and 750. Let's narrow down our interval again. And in seventh approximation, so we narrowed down it again, and it is like 2.7342. It is 7342. We done it. Then I will go back again. I will go next in my eighth approximation. It is 7342 and 7421. So now I am not using 2.75. I will use 2.7421. And I am running this one again. My code. My root is somewhere here. In my ninth, 10th, 11th, 12th, 14th, 15th, if I keep doing this thing, then ultimately I will reach very close to this root. So now in here, I stopped after 8 approximation and somehow we reach 2.7381. So by visualizing this particular graph in here, I can say that my root lie between 2.738 and 2.742. Then I'm gonna I'm gonna change it in here 7380 and 7420. Let me run it again. Now, excuse me. Now my interval is narrowed down again. So what if I do it like 2.740 and maybe 2.741? Okay, 2.7 2.740 and 2.742. Like let's just now up to two decimal places, 2.74, 2.74. My point, I can estimate my root. And then if I want to do it further, I can say that my root lies somewhere 2.7400 and 2.7410, somewhere like in between. So 70, 7410, 7410. I will just apply that here. And students, now you can see that your left tick mark on x-axis 2.7400, 2.7404, 2.7408. So until three decimal places, you are predicting very good. Your answer is correct. Let me take another iteration, and we are almost like 12th iteration almost. And then let me check 2.7404, 2.74 and 04 and 2.7408, and run everything. Then I have reached in here. Then I can see that my root is between 2.7406 and 740806. I run it again. And then until maybe 74060 and 74070. So 7407060. And I run it again. So I am keep doing this thing. Now you can see that until four decimal places, you get the same digits in here, like same number 7406, 7406, 7406, and it is 0, 4, and 8. Now I can change the interval and 74064, 74064, and 74068. And I get the value in here. So if I keep going, keep going, keep going, I will get closer. So I will stop in here that I somehow estimated until four decimal places. I estimated correctly. So if ever you want to locate your this particular point, so you can just make a point by using points function in R, points. Let's say let's say let's just deactivate it for now because they are useless now. So the point, so I reach in between this line. Let's just take this value as x. I need to put the x value and y value. So the y value will be 0. And let's just make the size of the point should be 2. and PCH mean point characteristics or point type. I will tell you later how you can find this one. I will just put it 20, and maybe color should be equals to red, or maybe you can just say like, I don't know, maybe orange and point. So somewhere here. So I can just try to like 74064, and this is 64, this is 66. So let's just try 3 in here, and let's check the point where 6. Oh, I think it should be 65, not 3. 6. So I am just close enough, right? So I'm just gonna plot it again. If you want to plot a line, so just activate one of them, Control Shift C, and put this one in here. And now if you run this one, it will exactly pass where you pass the point. So somehow this is our answer. This is our answer. But wait a minute. Let's try to, in here, you can see that this point is not exactly on this line. But once you will make the interval 2 and 3 back to your original one and run your code, now you will see that my point is exactly somewhere over there. So until like 4 decimal places, I get the correct answer in here. So that's it for the bisection method. And in this video, I tried that you try to visualize what are the roots and how we try to narrow our interval to reach to our root. Okay, there is an alternative way which is maybe new or maybe simpler, but maybe later on we will talk about that alternative technique. Okay, I will just copy it somewhere here. If we have the same question again, this is alternative way, okay? Instead of just writing like in previous, we write y is equals to this one. There is another way that we create a function by saying that my function and my variable is x. So x is equal to x log tan this one, and I create a function. So I say, then what I'm gonna do that I will create an interval again between 2 to 3, and let's say take it the value of x. All right. So I can find the value of y by just simply f of x. If I run this one, if x is this, y is equals to this. This is another way you can. Also, for example, you don't want for a sequence, just turn it off if you want f. So just write f of 1. What is f of 1? You will get y. Let's say it is y1. F of 2, y2. F of 3, y3. You can create 1 point and 1 point. But it is somehow similar when you activate this sequence. it has 2 and 3. So it will give you f of x if it will give you for the whole sequence, not for one point, but it will give you for a whole sequence. Also, one of the questions during the class, one student asked how we can get the root. So to get a root, there is an easy function. We call it uniroot. What we have to do that we have a function f. Once you say that f, this is your function. So you give the lower and upper values and dollar and the root. Just run this code. You will see your answer is 2.740646. So in here, we are somehow 2.7407, but in here it is 6. So somehow we are close, 74065. Somehow this answer was in here, and this answer was pretty close. So this is how the bisection method in R works. So please let me know if you have a question. So that's it for today. Bye bye.